At 13.5 nanometers, extreme ultraviolet radiation is absorbed by almost all matter, including air and traditional glass. This physical property necessitates a complete high-vacuum environment for the entire lithography process. Because refractive lenses absorb these photons, all optics must be reflective. These mirrors utilize Bragg reflection through multi-layer coatings of molybdenum and silicon, each layer only a few nanometers thick. The light generation begins with a generator firing 50,000 droplets of molten tin per second. Each droplet is 50 micrometers wide and travels at 60 meters per second into the vacuum chamber. A carbon dioxide laser fires a low-power pre-pulse to hit the flying droplet. This impact flattens the spherical tin into a thin pancake shape to increase its surface area. Immediately after the pre-pulse, a high-intensity main pulse strikes the flattened disk. This pulse ionizes the tin, creating a plasma reaching 500,000 degrees Kelvin. The highly ionized tin atoms emit photons across a wide spectrum. A specialized collector mirror then captures and focuses the specific 13.5 nanometer wavelength needed for lithography. The plasma creates debris that can damage the collector. A flow of hydrogen gas acts as a buffer, while chemical reactions convert tin into stannane gas to be pumped away. Filtered light passes through a small aperture called the intermediate focus. This point separates the high power source from the delicate illuminator optics, acting as a pressure barrier. Each molybdenum-silicon pair reflects only a fraction of the light. By stacking 40 to 50 pairs, constructive interference achieves a total reflectivity of approximately 70% per mirror surface. Mirror surfaces must be accurate within the width of a single atom. Any deviation larger than 0.2 nanometers would cause significant phase errors and blur the final image. Unlike traditional transparent masks, an extreme ultraviolet mask is a multi-layer mirror. A tantalum-based absorber layer is patterned on top to define the circuit features. Light hits the mask at a 6-degree angle. Because the absorber layers have physical height, they cast tiny shadows that must be compensated for during the design phase. A pellicle protects the mask from particles. It must be thinner than 50 nanometers to remain transparent to extreme ultraviolet light while withstanding intense heat from absorbed radiation.
The system uses a step and scan approach. The mask stage and wafer stage move in opposite directions with extreme precision, synchronized to within a fraction of a nanometer. Resolution is limited by the wavelength and the numerical aperture. Increasing the numerical aperture allows the system to capture higher-order diffraction patterns, enabling smaller feature sizes. High-energy ultraviolet photons strike the photoresist, triggering the release of secondary electrons. These electrons initiate chemical reactions that change the solubility of the resist material. Modern 3-nanometer processes often use metal oxide resists. These contain heavy atoms like tin, which absorb photons more efficiently than traditional polymer-based chemically amplified resists. At these scales, the low number of photons leads to stochastic variation. This photon shot noise causes random fluctuations in the pattern edges, known as line edge roughness. The depth of focus in extreme ultraviolet lithography is very shallow. Sensors map the wafer surface topography in real time, adjusting the stage height to keep the image sharp. A modern scanner processes over 170 wafers per hour. Dual stages allow the system to measure one wafer while the other is being exposed to maximize productivity. High numerical aperture systems use anamorphic optics, which provide different magnification factors for the horizontal and vertical axes. This compensates for the steep angles required by the mirrors. Absorbed energy generates significant heat within the vacuum. Specialized cooling systems using hydrogen gas and water-cooled plates maintain the mirrors at a constant temperature to prevent expansion. Computational lithography distorts the mask patterns to account for diffraction. These intentional distortions ensure that the final printed shape on the silicon wafer matches the intended circuit design. Printing 3-nanometer features requires aligning multiple layers with an accuracy of less than 1 nanometer. Any misalignment would cause short circuits or broken connections in the final chip. To eliminate friction and vibration, wafer stages float on magnetic bearings. This allows for accelerations of several times gravity while maintaining nanometer-level positioning accuracy. Turbomolecular pumps maintain a pressure of 10 to the power of -7 millibars. This prevents even trace amounts of residual gas from absorbing the light or contaminating the mirrors. Increasing throughput requires more powerful light sources. Current systems utilize carbon dioxide lasers with over 20 kilowatts of power to generate enough photons for high-speed exposure.
Hydrogen radicals are introduced to chemically clean the optics during operation. They react with carbon and tin deposits, forming volatile gases that are safely removed by the vacuum system. Defects in the mask can be invisible to deep ultraviolet light. Actinic inspection uses the same 13.5 nanometer wavelength to find flaws hidden within the multi-layer mirror structure. Local uniformity is critical for transistor performance. Stochastic variations in the resist and light source must be tightly controlled to ensure every transistor on the chip behaves identically. Roughness on the mirrors causes light to scatter, creating a background fog known as flare. This reduces image contrast and must be minimized through advanced surface finishing techniques. When too few photons land in a specific area, resist lines may accidentally merge or break. These stochastic defects represent the fundamental limit of scaling with current resist technologies. Interferometers constantly monitor the shape of the light waves. If distortions are detected, adjustable mirrors to form slightly to correct the wavefront and maintain focus across the entire exposure field. Extreme ultraviolet lithography enables the dense packing of thin field effect transistors. This allows for 3 nanometer logic gates and high-density memory cells used in modern processors. A single lithography tool consumes over 1 megawatt of electricity. Most of this energy is used to power the drive laser and the extensive cooling systems required for stable operation. Since light passes through the pellicle twice, its transmission rate is double-counted. A pellicle with 90% transmission actually reduces the total light reaching the wafer by nearly 20%. Researchers are investigating high-K materials for mask absorbers. These materials block light more effectively at thinner dimensions, reducing the shadowing effects that limit resolution in current systems. Laser sensors detect alignment marks etched into the silicon. This feedback loop allows the stage to position the wafer with sub-nanometer precision before each pulse of light. In chemically amplified resists, acids travel through the material to catalyze reactions. Controlling this diffusion length is vital to preventing the blurring of 3 nanometer features. Small changes in laser energy, or dose, significantly impact the final feature size. Precise pulse-to-pulse energy control is mandatory for maintaining consistent critical dimensions across the wafer.
Scattered light metrology tools measure the wafers immediately after processing. This data is fed back to the scanner to automatically correct for drift in the optics or stage alignment. Optics are made from glass ceramics with a thermal expansion coefficient near 0. This ensures the mirrors do not change shape even when subjected to intense radiation during long production runs. The illuminator optics shape the light into complex patterns like dipoles or quadrupoles. This off-axis illumination improves the contrast for specific types of circuit patterns on the mask. Next-generation high numerical aperture systems use a larger lens that reduces the exposure field to half the size of current scanners. This requires stitching multiple fields together on the wafer. The resolution of the resist is determined by the travel distance of secondary electrons. Shorter paths result in higher resolution, but require higher energy photons to initiate the process. Even with extreme ultraviolet light, some features require double patterning. This involves splitting the design into 2 separate masks and 2 exposure steps to achieve even higher density. The sum of all errors, including overlay, stochastics, and lens distortion, is the edge placement error. Keeping this below 1 nanometer is the primary challenge of the 3 nanometer node. The interior of the scanner must be cleaner than a medical operating room. A single particle larger than 10 nanometers can ruin an entire chip if it lands on the mask. Future lithography will explore wavelengths shorter than 13 nanometers or hypernumerical aperture systems. These advancements aim to keep the semiconductor industry on the path of Moore's law. Extreme ultraviolet lithography represents the pinnacle of optical engineering and plasma physics. It allows the mass production of billions of transistors, each smaller than a human virus, on a single chip.